Yes, good afternoon. Today we would like to discuss another case of a closed form solution. Okay. Did we give numbers to the topics? 24. Okay. And here we consider such a beam. Actually, I found this material especially at the request of Mr. Dale. He asked me if the solution that we found was the only exact solution or not. So I found one more exact solution. And that is like this. There is this beam that is simply supported, and here it is free. And this beam is vibrating here, so this is length L. And so W at x equals L here is F times cosine omega t. F is an amplitude of vibration. Omega is the frequency of excitation. So this end is vibrating like this with some frequency omega. And we are interested with what transpires with the beam. So this is a question. So beam's vibration we can write down again as EI, d4W dx in force power plus rho A d2W dt square equals 0. And this small w is written in terms of capital W of x and cosine omega t. Maybe I will finish this topic and then you can do that. Or maybe mine will be 10 minutes approximately. You want to now? Okay, then we will do that if you want. Okay, fine.
We're going to put it on that screen, on the car screen, see if we can get it going.
Fine. Can I continue in the meeting? Okay, fine. Okay. So then the solution is, not solution, but let us write it down, d4 capital W dx in force power minus rho A omega square capital W equals 0. Then we divide it by EI, and we get d4 capital W dx in force power minus rho A omega square divided by EI capital W equals 0. And this, if you remember, we denote by alpha in force power. Alpha in force power. And we get d4W dx in force power minus alpha in force power W equals 0. Now, solution of this differential equation, as we know, is capital W of x equals C1 K1 alpha x plus C2 K2 alpha x plus C3 K3 alpha x plus C4 K4 alpha x. Okay, so this is page 1. Now, we would like to satisfy boundary conditions. Now, capital W at 0 equals 0, and W second derivative at 0 equals 0 for simply supported and. Okay? So, therefore, look please, when I substitute here x equals 0, then these k2, k3, k4 vanish. K1 equals 1, so C1 must be equal 0. And second derivative of K3 equals K1. So then, when I calculate second derivative, I will have C3 alpha square K1. So therefore, this C3 is also 0. Okay? So what I'm left is W of x equals C2K2 alpha x plus C4K4 alpha x. Now, what are the conditions at x equals L? First of all, function equals capital W equals f. Yeah, function itself equals f, small f. This W should be multiplied by cosine omega t, and this is multiplied also by cosine omega t. So we have C2K2 alpha L plus C4K4 alpha L equals f. And then second derivative of W equals 0. So let me write down here should be L. W at L. Second derivative equals 0. So W's second derivative at L equals alpha square C2. Now K2's first derivative is K1. Second derivative then equals K0 or K4. K4 alpha L. Plus, that is K3, K2. C2, K2 alpha L. Now, so from these two equations, from this, okay, this equals 0. From here I find that is C2, this is C4. Yes. So C2 equals from here minus C4, K2 alpha L divided by K4 alpha L. That is C2 from this equation. Then I substitute this into first equation. So I get C2 equal minus C4, K2 alpha L, K4 alpha L, then K2 alpha L, plus C4, K4 alpha L, equals F. So from here we can get C4. C4 equals F divided by K4 alpha L minus K2 alpha L squared divided by K4 alpha L. Or this equals F times K4 alpha L, K4 square alpha L minus K2 squared alpha L. So that is C4. and C2 equals minus C4 K2 alpha L divided by K4 alpha L, and this equals minus F K2 alpha L K4 square alpha L minus K2 square alpha L. So final result then equals W of X equals C2 K2 alpha X plus C4 K4 alpha X, and this equals C2 K2. So it will be minus F K2 alpha L K2 alpha X, then plus C4 plus F K4 alpha L K4 alpha X, and this whole thing is divided by K4 square alpha L minus K2 square alpha L. So W of X equals, we can write down just F. First term I can write here, this K4 alpha L K4 alpha X minus K2 alpha L K2 alpha X K4 square alpha L minus K2 square alpha L, okay, which is a closed form solution. And now the question is for when do we have a resonance? Question. Answer. When denominator vanishes. Yeah, that means K4 square alpha L minus K2 square alpha L equals 0. When denominator is 0, then W of X goes to infinity. Say it again. So that means that, look please, that means that if xi, now this expression is known to us. Is known to us. This is a frequency expression for simply supported column. Okay, this expression. Indeed, K4 square alpha L minus K2 square alpha L equals sine alpha L hyperbolic sine alpha L. And that means that when alpha L equals pi, or 2 pi, etc., then this, we have a resonance. So also this column is not, this beam is not simply supported. But when omega goes to omega pi or 2 pi or 3 pi, etc., omega k, natural frequency of a simply supported beam, resonance takes place. See, so it's another closed form solution.
We have a possible solution, but what it's going to require is a hard start, a reboot, and shut down the whole system. So if you want to go through the steps and module and then break for 5 minutes or something, that's what I.
Fine. Do you want us to break for a few minutes?
Whatever you want. Yeah, we'll need at least a few minutes because we're going to shut everything down and restart it.
I see. Okay, a few minutes and it is
Whenever
okay.
you're.
Okay, I will assign homework and then we will do.
If that's okay.
Yes, that is okay. It's okay. So I would like to assign the homework. This gives us to a possible homework. So that is clamped free beam. Length is L, and this here vibration this W of L, small w of L, is varying as F sine omega t. Okay? Find the expression for W of X, and when does the resonance take place? Okay, maybe in a few minutes we can. Yes. Okay, we would like to say, okay, that is topic 25, Galerkin's method. Now, solving the vibration problem may be very difficult if at all possible for the beams of variable cross-section. For example, beams like this, say that is simply supported, or beams like this, say imagine this is clamped free, etc. So here then governing differential equation is like this. Not as we wrote EI d4w dx square plus rho a d2w dt square equals 0. So not this equation. But a different equation. And that is d2 dx square EI d2w dx squared plus rho a d2w dt squared equals 0. Because this is an expression of the moment. Okay, mz equals ei d2w dx squared. And when ei is constant, we get this equation. For ei equals constant, we get this equation. But if ei is changing, say is a function of x, then we have more general equation. Okay? Then functions k1 alpha x, etc., do not apply to this case. Do not apply. Yes, please. Say it again. Second term is the same, of course, because that is an inertia term. Say it again. Yeah, A can be changing, but it is just a product. There is no differentiation. This could be changing. So if you want, I can write down in the most general form. Most general form of the governing differential equation would be d2 dx squared e of x I of x d2w dx squared plus rho of x a of x d2w dt squared equals 0. So that is the most general form. Now, this equation cannot be solved exactly for any variations. So the question is how to deal with this. So the answer was given in answer to this question. This is the question. By Bubnov, 1913, he gave an idea. And Galerkin, 1915, suggested this method itself. Now, what they say is as follows. Look, please. Before we continue, I would like to denote something. If we have two functions, say psi1 and psi2, psi1 of x, psi2 of x, okay, then we can denote integral between 0 to L, psi1 of x, psi2 of x dx. This can be denoted like short notation. The short notation is psi1 times psi1, and then parentheses. So that is a notation. I would like that we agree with this notation. Actually, this notation is like inner product or dot product. What is a dot product? If I have vector A, AXI plus AYJ plus AZK, and vector B, equals bxi plus byj plus bzk. Okay? Then dot product, if you remember, equals sum of products of coordinates ax bx plus ay by plus az bz. So integral is also sum. Integral is sum. So it is actually sum of the products. So therefore, this can be called as an dot product, or better notation is inner product. Okay? So now what Galerkin says is as follows. Look, please. Did we write this? Yes. So we will start from this equation. So Galerkin says, let us choose some function psi1x. Choose some function psi1x that satisfies boundary conditions. That satisfies boundary conditions. W1 is some W1 is some constant. And we approximate solution. This is approximation. Please write down, this is an approximation. This does not satisfy the governing differential equation. This function. It satisfies only the boundary conditions, nothing else. Now I substitute this into the differential equation. Look, please. Please write it down first. Maybe I will explain it. When I substitute this in the differential equation, naturally this expression is not zero because this does not satisfy the equation. So therefore, what I'm getting is something that is could be called error. This is an error. So this epsilon is not zero because this psi1 does not satisfy the governing differential equation because I'm just picking some function that satisfies only boundary conditions. Now I got psi. Then Galerkin says, you know what? This approximation this is an error. But this error, we would like to be not see from psi1 direction. So this error should be small, so to say, in such a manner that when I multiply this error by psi1 and integrate, this integral should be zero. Now, this very often happens in human relations. How does it happen? Say, for example, child maybe misbehaves, so he makes an error. But mom, from her benevolent eyes, overlooks this error. So she does not say anything. She just passes it by, so to say. So that is something like that. Galerkin says this is an error, but when I look from the point of view of psi 1, this error is 0. This, so to say, projection of error in psi y direction is 0. That is his demand. This will make error smaller, so to say, because I don't see error in psi 1 direction. Now, psi 1 direction is a very important direction. Why it is an important direction? Because psi 1 is a function that I chose. I said that W is approximated as psi 1. Then what we get actually is as follows. Look, please. This is epsilon, that is EI, force derivative of psi 1. I multiply it by psi 1 and integrate from 0 to L. So this is then a number. This is a number. Then it is minus rho A, psi 1. This is multiplied by psi 1 and integrated. Then times omega squared, must be 0. So then omega squared equals this expression. It equals EI, psi 1 force derivative, times psi 1, divided by rho A psi 1 times psi 1. So this is numerator, this is denominator, this is omega 1 squared, approximation of the first natural frequency squared. Question, how good is this approximation? Can I take this out? Then maybe question 2. And question 1 is how to use it. How to use this approximation. Okay, so let us consider some example if you want. Imagine EI itself equals EI 0 times 1 plus sine pi x over L. Rho A, imagine equals rho A sub 0. Okay, so let us write here beta. 1 plus gamma sine pi x over L. Okay, beta and gamma are constants. Okay. Beam is simply supported. At both ends. So then governing differential equation is like this. d2 dx squared EI 0 1 plus beta sine pi x over L d2w dx squared minus rho A, but this rho A equals rho A 0 1 plus gamma sine pi x over L, omega square W. This equals 0. So for approximation, W equals sine pi x over L. That is the first mode of uniform beam. Satisfies all boundary conditions. Okay. Now I substitute this here, and then I multiply by the same thing, so that I'm getting, look please. Look please, and I integrate. Integral between 0 to L. Second derivative of x squared. EI 0. 1 plus beta sine pi x over L. Okay? Then it will be, second derivative of this will be minus pi square L square sine pi x over L. Okay? Then I'm finishing this. I'm close to this. I differentiate it. I multiply this by psi, sine pi x over L dx. Then I have second thing, minus rho A0, integral between 0 to L, 1 plus gamma sine pi x over L. We multiply this by sine pi x over L, and here is omega square, of course. Dx equals 0. That is when I multiply again, yes, by psi. So from here I get omega square. Omega square equals some numerator divided by denominator. So we got an approximation. For all values of beta and gamma. Beta and gamma can be anything, 1, 2, 3,000, whatever we want. So we get first frequency approximation. That is how we do it, so to say. Pay attention, I substituted this sine pi x over L, this approximation, in the differential equation here. Then I multiplied by sine pi x over L, that is by psi. Okay? The same here, I substituted this approximation, W. Okay? And I multiplied by sine pi x over L. Oh, I forgot, I wrote this, but I forgot this W here. I had to substitute W approximation, and then I multiply again. Sorry. Any questions here? Now I will answer the question how good this approximation is. Are we done? Or not? Yes. accuracy of Galerkin approximation. So consider uniform beam. So beta equals 0, gamma equals 0. So the governing differential equation is EI d4w dx in force power minus rho a omega squared w equals 0. So we know exact solution. Exact solution equals omega 1 square equals EI pi over L in force power divided by rho a. Okay, I substitute here. We substitute approximation. W equals sine pi x over L. Okay, let us substitute there. We get EI, force derivative, pi over L in force power. Maybe. So we will write the equation like this. EI d4 dx in force power sine pi x over L minus rho a omega square sine pi x over L, that is epsilon. Yes, I substituted this here. So I did not get 0, I got epsilon. Now I'm writing epsilon times psi 1 equals, that is actually psi 1, equals epsilon times sine pi x over L equals 0. So we get EI force derivative pi over L in force power sine pi x over L minus rho a omega squared sine pi x over L. This should be multiplied by sine pi x over L, and that equals 0. So I get from the first term integral between 0 to L EI pi over L in force power sine square pi x over L dx minus rho a omega square sine square pi x over L dx equals 0. This equals, this can be taken out of integral, EI pi over L in force power. Integral from sine square pi x over L is L over 2. Minus rho a omega square, L over 2, this equals 0. So from here, this L over 2 and L over 2 are canceling. Omega square equals EI over rho a pi over L in force power. We got exact solution. So Galerkin approximation gives extremely good approximation for the cases when exact solution is available. It's a very, very accurate method. See, by another means, we got exact solution. Any questions? Yeah, the question, another question. What about finite element method approximation?